Now today we're going to start a new paper, and a couple of the questions that are here are kind of like ideas that are based on the previous questions that we've done. So I think I've given you one question on trying to find the canonical momentum using the Lagrangian of a charged particle in an electromagnetic field. So that question, I just gave you the derivation. So if I have time today, I will kind of like expand on that derivation and actually kind of like help you commit to memory. Okay, so let's move to the first question. Okay, so every time, I think this is like a standard pattern that they have. They start off with trying to ask you to find eigenvalues. Okay, so the eigenvalues of the matrix cos theta, sine theta, minus sine theta, and cos theta will be, okay, don't try to diagonalize this like I said last time. Try to use tricks. Okay, so the two tricks that are there for you are, when you take the trace, you should basically get the sum of the eigenvalues. Trace is equal to sum of eigenvalues. Okay, and the determinant of your matrix, okay, the determinant of your matrix is equal to the product of the eigenvalues. Okay, so now let's look at the options. Okay, so these are the options that are given to you: e to the power of I theta, e power minus I theta, sine theta and cos theta, minus sine theta and minus cos theta, e to the power of theta, and e to the power of minus theta. So now let's just look at the trace part of it. Okay, so now we know that the trace is equal to 2 cos theta from the matrix. Okay, so when you add up your eigenvalues from these results, you should be able to get something like this. Okay, you should be able to get 2 cos theta. So now we know that it's not going to be these two, because when you try and add up these two, they're not going to simplify to 2 cos theta. You know that's not going to be these two either. So let's just start off with the first one, e power I theta plus e power minus I theta. Okay, so e to the power of I theta is what? You basically have, let's say, cos theta is equal to e to the power of I theta plus e to the power of minus I theta divided by 2. And sine theta is equal to e to the power of I theta minus e to the power of minus I theta divided by 2i. Okay, so these are the formulas. I think you should be pretty familiar with them because we've used them a lot of times. So basically now when you do 2 cos theta, you end up getting e to the power of I theta plus e to the power of minus I theta. Okay, so this is going to be your answer. It's going to be option A. Okay, so just keep this in your head. Last time we had something like this. They asked us which were those eigenvalues, and we had to use this. Okay, determinant is equal to the product of the eigenvalues. This time we're basically using trace is equal to the sum of the eigenvalues. Okay, so trace is equal to 2 cos theta. This is what you have. This is your answer. Okay, so now let's look at this. Okay, this is basically something that you've done in your Laplace transforms. Okay, so Laplace transform of sine, hyperbolic sine kt. Okay, sine hyperbolic kt. What do you end up getting? Okay, so how do you define your Laplace transforms? Let's look at the definition. Okay, so for a function f of t, okay, this is basically how you can write your Laplace transform. F of s is equal to integral from 0 to infinity e to the power of minus st f of t dt. Okay, so this is the form of your Laplace transform. Now, let's look at how we can implement it. Okay, so now you have to know the formula for sine hyperbolic kt. Okay, so how I remembered it is when you have a h, you don't have anything on the top. Okay, so you don't have an I on the top. Usually when you write your cos theta, okay, so cos theta is written as what? E to the power of I theta plus e to the power of minus I theta divided by 2. Okay, so this is what you've got. Now, if you look at your hyperbolic, you do not have an I on top. Okay, basically it's the same thing, but without the I on top. Okay, so it's similar to this without the I on top. And if you are looking at your sine theta, you basically have a 2i. So it's basically like canceling out all the i's that you have. Okay, all the imaginary numbers that you have. So that's like the trick to kind of like, if you forget about it, you can remember it this way. Okay. So you have 1 divided by 2 e to the power of minus sine minus kt divided by minus s minus kt. That's your integral of your exponential. Okay. You have e to the power of minus s plus kt minus s plus kt 0 to infinity. So this is, you have to calculate this out. So what do you have here? When you put up your minus infinity, you get a 0. Okay. When you put up a 0, you get 1. Okay. So you get minus of this one. Okay. So you basically have a 1 divided by minus of s minus kt. Here you again put an infinity. So you end up getting e to the power of minus infinity. That should give you 1 divided by infinity, which is 0. So you don't include that term. Then you have negative already here. So this is like your lower limit. Okay. That's why there's a negative here. And then you have, so let's just move on with this. So you have L of sine hyperbolic kt is equal to 1 divided by 2k. Okay, so you multiply this and this, you do some kind of algebraic manipulation, and you end up getting a k divided by s square minus k square. Now, the important thing to remember here is that your s square should be greater than your k square. Okay, so that's something important to note. They really never put that there. So let's just look at our options now. You have option B. Okay, so that's k divided by, okay, I think I goofed this up. This is supposed to be k not f. Okay, so this is supposed to be k. Okay, so you have k divided by s square minus k square. Now let's go to this. Okay, so now what I would suggest you do is you kind of like try and by heart the recurrence relations. Okay, try and do them once. How do you get your recurrence relations? Basically, you have these generating functions that are given to you for each different type of differential equation. Okay, so you use those those generating functions. Either you divide them with respect to x or t. It should be a function g of x comma t. It would look something like this. You would have something like this, g of x comma t. Sometimes you differentiate it once with respect to x, another time you would differentiate it with respect to time, or you would differentiate it twice with respect to x or twice with respect to time, and then you get a lot of various combinations for your you would get it for your Bessel, your Hermite, your Laguerre, and your Legendre. Okay, so now let's look at all these recurrence relations. Okay, so I'm going to talk to you about a couple of primary recurrence relations. Okay, so you have 2n plus 1 x p n of x is equal to n plus 1 p n plus 1 of x plus n p n minus 1 of x. So this is a really nice formula. Okay. So if you notice, you realize that the present polynomial can be written in terms of successive polynomials. Okay, so you can write it in terms of the one in the front and the one at the back. Okay, so the current polynomial can be written as one forward to it and the one backward to it. Okay, so this is called something called the Bonnet's recursion formula. I think I've done a video on this. Okay. We kind of like had to do a seminar for one of our computation physics classes, and I took this part of that. Okay, so if you want, you can go check that out. Okay, so here, this one is called the Bonnet's recursion formula. Now let's move on to the next one. Okay, so how do you remember that this is the Bonnet's recursion formula? Basically, you don't have derivatives involved in it. Okay, you only have derivatives involved in the rest of the recurrence relations that you have. Okay, so these are the several types of recurrence relations. Okay, so there are a couple of other recurrence relations that you get. I'm sure you might have done these, okay, on your own. And then let's look at this formula. A particular formula that I would look at is this. Okay, so now instead of n, I will put this as L. Okay, so let me just write this. P prime L minus 1 of x should be equal to x P prime L of x minus L P L of x. Okay, so this is how it's written there. Now you have to be a little more careful about this, because they can change the variable of n, and you might be used to that particular thing. Okay, so let's look at what's here. Okay, so basically you have this, right? You have an x p prime L of x is equal to, this guy comes this side. Okay, so you basically have L p L of x plus p prime L minus 1 of x. Okay, so now the thing that you're supposed to be careful about is this. They've written that it is not true. Okay, so your automatic instinct is to tick out the ones which are true. Okay, so this is true. Okay, now I will show you how the Hermite looks. Okay, so I know that this is true, this is false, and this is extremely confusing because there's only a small change in sign over here. Okay, and this is also not true. Okay, so they've asked for the ones which are not true, so that's going to be option C and D. Now in KSET questions, there are no multiple correct options for you. It's just one correct choice, okay, that you have. So they've kind of given marks for both these options, C as well as D, in this set of questions. Okay, so let's just go through the other recursion formulas. Okay, for your Bessel polynomials, you have n by x jn of x, jn prime of x is equal to jn minus 1 of x. And then you have n divided by x jn of x minus jn prime of x is equal to jn plus 1 of x. You have 2n by x jn of x is equal to jn plus 1 of x minus jn minus 1 of x. So I think the next one that you have is kind of like the one that's confusing. Okay, so this is basically what, let's just write it down, jn minus 1 of x minus jn plus 1 of x is equal to 2j prime n of x. Okay, so let's go back and look at it. Okay, so now you realize in your Bessel function, the only difference was that negative sign. So you won't even look at it. You see these two terms and then you'll just tick it off. So it's, I think you should probably write these formulae down, stick it on your wall, and every time before you go to bed, you read it once. And then by the end of the, like by the time you start your exams, or by the time you probably have a year left, okay? So by the time that happens, you'll be like, you know it really well. Okay, so let's move on to the next set of equations that you have. You have your Laguerre polynomials. Okay, so I think Laguerre means like war or something in French. Okay, so that's nothing to do with this, but these are the set of polynomials that you have. Okay, so try to memorize them. And then you have Hermite, which was this. Okay, so I think I told you that this looked like it was true. And the other thing that you can note is one of these Laguerre polynomials looks exactly like the differential equation. Okay, so this is your H double prime, one of the recurrence relations looks like the differential equation, the Hermite differential equation. Okay, so, okay, let's move on to the next question. Which of the following is not correct with regard to normal distribution? Normal distribution is basically a Gaussian distribution. Okay, so let's look at each point. Okay, and let's just see, whenever there's terms like not, okay, whenever there's terms like not true and things like that, you should be very careful about it because you end up ticking what is true. Okay, so it is a continuous distribution. This is true. It is a bell-shaped curve symmetric about the mean. Okay, so this is how your Gaussian distribution looks, and it is symmetric about the mean, so this is true. Its curvature depends on the value of the standard deviation. So you have sigma, this is true. Its curvature depends on the value of the mean. Okay, so this too is true. Okay, so I will tell you why it is in a moment. Okay, the mean of the mode coincide. Okay, the mean and the mode coincide. This is true. The mean, the mode, and the median coincide in the case of normal distributions. The mean and the median do not coincide. Okay, this is false. The points of inflection of the curve at x equal to plus or minus sigma. Okay, so it occurs at about x equal to plus or minus sigma, which is also true. So you realize there's just one thing that's not true here. Okay. So now I think this wasn't challenged. Okay, this question wasn't challenged, and they have kind of given the option as A. Okay, so if you realize the option that is false is only 6, and they've said which is not true, right? So that means the only option that is false. Okay, so that's basically 6. Now I think they've ruled it out by using these two terms. Okay, so if you look at this, the quick way to kind of like do this problem is, it is a continuous distribution, you know that. Okay, and they've said which is not true. Okay, but you know this is true. Okay, so whenever you have one, you eliminate those two options. Okay, so the second one is, it is a bell-shaped curve symmetric about the mean. So when you say it is a bell-shaped curve symmetric about the mean, what do you have? You have 2, 3, 4, and 7. Okay, so here you basically end up having something that is true, and they've asked for not true. So this term gets cancelled, and then everybody starts to tick this. So I think that's why this wasn't really challenged, because everybody knows these two properties of normal distributions, but they don't know the specific properties other than these two. Okay, so about the curvature and things like that. So the mean and the median are basically two things that tells you about any probability distribution. Okay, so in the case of your Poisson distribution, your mean and the median, the mean and the standard deviation. The mean and the standard deviation are the two things that tell you about any probability distribution. So in case of your Poisson distribution, I think we've discussed about this. The standard deviation is basically the mean. Okay, the standard deviation and the mean are equal for your Poisson distribution. Okay, so now let's go to the next one. Okay, so a normal or Gaussian or Gauss or Laplace distribution is a type of continuous probability distribution for a real valued random variable. A normal distribution is sometimes informally called a bell curve, but there are other distributions which are bell-shaped as well. So saying that that is the only bell curve that is there, that is the name of the curve, is not really nice. Okay, so the graph of the normal distribution depends on two factors. One is the mean that you have, and the other one is the standard deviation. The mean of the distribution determines the location of the center of the graph, and the standard deviation determines the height. So mean basically tells you where the peak is going to be at. Okay, so let me just denote that as x average. Okay, these notations may vary from book to book. And the other one is basically going to tell you about the height as well as the width of the graph. So basically it's going to vary the curvature. Okay, so the shape of the entire bell curve is basically going to depend on these two parameters, and both of them can vary the curvature of the curve. Okay, so that's why this this statement which says which is that one, fourth statement. Okay, they said that is not correct, but it's actually correct. The curvature depends on the value of the mean as well. Okay, so you realize the center at which you have your peak is basically depending on the mean value. Okay, and based on that, the curve's depth or the curve's steepness can be like different. Okay, so now let's look at this. The general form of the probability density function is f of x is equal to 1 divided by sigma root of 2 pi e to the power of minus 1 by 2 x minus mu divided by sigma whole squared. Okay, so mu is basically your mean here. Okay, and it is also the median as well as the mode. Now let's discuss about what your median and mode mean. Okay, so if you have a set of numbers, say like 2, 5, 9, 8, 8, 9, 6. Okay, so this is a thing that I have. Now I will cut off each value. I want to find the median of this. Okay, so I'll cut off each value from the side. Okay, and then what I will get is my median is 8. Okay, so median is equal to 8. Now if there were two numbers, okay, and if I cannot, if the entire set of numbers here, you basically had an entire set of numbers which were basically how many did you have? 1, 2, 3, 4, 5, 6, 7, 7 numbers. Okay, so you had 7 numbers, and this is a set of not even numbers, I cannot say that. Basically the numbers, the number of numbers that are there is odd. Okay, so in that case, you just have one median. If the number of numbers that are there is even, say, like if it was, if I had another number, say 5 here, so basically when I scratch this out, I get 8 and 8. Okay, so this probably wouldn't have been a very nice example if there were to be 5 and 4 as your two numbers that were there in the middle. So this would be basically 4 plus 5 divided by 2. That should give you a 4.5 as your median. So median is what is there in the middle. Okay, so that's one way you can think about it. If you have two numbers in the middle, then you take the average of those two. Okay, so basically if you have an even set of numbers, then you take the average of those two in the middle. Okay, so now let's go back to the other example that we were talking about. What were we talking about? Let's remove this guy. Let's remove all this. Okay, so let's remove all these crosses. Let's remove these as well. Okay, so now we want to know what the mode is. So mode is basically the value which has repeated the maximum number of times. Okay, so here you basically have two modes. Okay, you basically have two 9s repeating and you have two 8s repeating. Okay, so you have your 9 repeating, that's one mode, and you have 8 repeating. So these kind of things are called bimodular. There are two modes repeating, so they're called bimodular. The Gaussian is particular about this. They are always unimodular. So they just have one mode, they have one median, and they have one mean, which all are the same. Okay. So now let's look at all of this. Okay, so I think you know this. Sigma is the standard deviation. Sigma square is the variance. The random variable with the Gaussian distribution is said to be normally distributed and is called a normal deviate. Okay, so the random variable is basically your x over here. Okay, so the points of inflection are basically the points where your curvature change occur, and they are basically plus or minus sigma. Okay, so the points where your curvature changes occur. Okay, so that's what you have here. Okay, so now let's look at this. So now let's look at this. Okay, so you have an f of x equal to x. Okay, I think I discussed about the Fourier series last time. Okay, is your x even or odd depends on the value of the interval that you have. Okay, so now if I plot this for you, you're going to realize, okay, let me just plot this for you first. You have 0, you have 2. Okay, so let's just put this here, and you end up having f of x equal to x. Then you have another interval 0 and 2 and 4. Okay, and then you have this. Okay, so basically you end up having x again. So you have -2. Okay, and then you have -4. Okay, so now if I reflect this along this path, if I put a mirror and reflect it, you put a mirror image here, and then you kind of like have something like this coming up. Okay, so that's not an even function. Neither is it an odd function because it doesn't come out to the other axis like this. Okay, so it doesn't even come to the other axis like this. So you basically end up having neither even nor odd, and that means what? It means more work. You need to calculate both your a sub n as well as b sub n coefficients, because none of them are going to be, none of them are going to be equal to 0. Okay, so now let's kind of look at this. Okay, so now the trick here is to not actually work this whole problem out. Let's just read through the problem and understand what they've actually asked us to find. If f of x is equal to x for 0 less than or equal to x less than or equal to 2, and f of x is expanded in Fourier series, then the constant term in the series is, what is it? So if you like really gone through Fourier series properly, okay, you will remember that there's just one constant term. Okay, so that's just a naught divided by 2. That is your constant term. Okay, so now let's move on to the description. So basically when they're saying this, you should automatically go on to say 1, okay, because that's the definition of your constant term. So let's just look at this. The Fourier coefficients A's are called your Fourier sine coefficients, okay, including A naught, the constant term, which is in reality the 0th cosine term. And your B's are called the Fourier sine coefficients. So the constant term basically has an expression like this, A naught divided by 2. Now the interval that I have is basically from 0 to L, okay, it's basically from 0 to 2. So I end up having to divide this whole, multiply this whole thing by 2. If I have an interval from minus L to L, I have to do this, okay? So I end up having 1 divided by L integral from minus L to L f of x dx, if that is the range, okay? If this is the range and if you have from 0 to L, this is your definition of your constant term. And also remember that the constant term includes this, okay? The constant term does include the 2. A naught is just not the constant term. You need to say A naught divided by 2. And this has particular significance because this value of your constant term is your average value of f of x. So now let's just calculate this for this problem, okay? So you had L was equal to 2, okay? So the interval was from 0 to 2. So let me just multiply this by 2. The function was x. So you integrated from 0 to, this is basically L, not infinity, okay? So I made a typo there, it's not infinity, it's L. And then I have an x and dx, okay? So let's cancel this off, 1 divided by 2, integral from 0 to L, okay? So I will just integrate it, x squared divided by 2, 0 to 2. Okay, so let's just put that in there. So you have 4, 2 squared is 4, divided by 4, you get 1. Okay, so now let's go back and let's kind of like analyze this whole thing. Okay, so let's go back. Okay, so what did I tell you? How do you draw this function? Basically, you draw it from 0 to 2, right? So when you take the average of these 2 points, where do you end up coming? You end up coming at 1. And this is called the constant term. Okay. Now let's go on to this. Okay. So if your f is periodic, this average value is the same for every period f of f. Okay. And therefore, the constant term in your Fourier series represents the average value of the function over the entire domain. Okay. So it's the average value of the function over one period of time. Okay. So now let me do the Taylor series expansion, which is quite simple, of sin x. So all these options that they've given is wrong. Okay, you don't even, I think you might have by hearted these Taylor series expansions or the Maclaurin series. Okay, what is Maclaurin series? Basically, it's called Maclaurin. Okay, the Maclaurin series is basically whenever you have the point at which you're doing this entire function, okay, trying to find out the value of this function is equal to 0. And that's what we're going to do here, okay? So you're not trying to find it at some random value, say A, you're trying to find it at 0. So then your Taylor series kind of like reduces to the Maclaurin series. Okay, so let's look at this. Okay, so I think you know how you can write your Taylor series up. So basically it's f of x is equal to f of a. Basically you're trying to express the function in terms of the derivatives. If you look at your Fourier series, you're trying to express the function in terms of your sines and cosines, okay? Here you're trying to express the functions in terms of your derivatives in your Taylor series, okay? So here you have an f of a. A is basically the point at which you're evaluating the series. F prime of a, first derivative divided by 1 factorial into x minus a. A is again the point at which you're trying to evaluate your series. And you repeat these, so on and so forth. So let me just show you a compact notation. So you have summation of n is equal to 0 to infinity f of n of a, f nth derivative of a, divided by n factorial into x minus a whole power n. Okay, so this denotes the nth derivative evaluated at point A, and n factorial denotes the factorial of n. Okay, so let's look at this, okay? So this is your Maclaurin series basically doing the same thing at the point 0. So your f kth derivative, I just put a different value here, kth derivative 0 divided by k factorial, okay, whole power k, and then you substitute 0 for everything that you had there, okay, previously. And basically you had an x minus 0 here, okay, so you had an x minus a that became 0. Again, this had an x minus a square, so a was 0, so that's what you do. And then you kind of like try and evaluate this out, okay, so you get x. Now you have to be careful about this, okay? So basically what are you doing? You're trying to find out, first you have to find out the derivatives, and then you need to do this. So you'll realize that when you're trying to find out the derivatives, whenever you have cos, you have a value. Whenever you have sine, it becomes 0 because sine 0 is 0. So let's start off with the first one. You had sine x, okay? So you had a f of 0, which is 0. Sine 0 is 0. You have an f prime of 0. That's basically your cos x, which is 1, okay? So you have no issues there. Then when you take the derivative again, you have a minus sine x, okay? Take the derivative of this one. So when you have a minus sine x, that turns 0. And then you have cos x, which is equal to minus 1. So you end up having a minus 1. Similarly, repeat this again. So you end up having plus sine x now, which is 0. And then that is 0. And then you do the derivative of the sine x, so you get cos x, and then you end up getting 1. So this is pretty simple to do. You really don't have to memorize anything much. All that you have to think about is when you're looking at Taylor series, the function is expressed in terms of derivatives. Okay, so that's what you're supposed to be looking at. So let's move on to this question. The value of the contour integral dx divided by z square z plus 3, where c denotes a unit circle z is equal to 1 traced in the contour clockwise direction is. Now, you have to be very careful about this, okay? Whenever I'm talking about things like Cauchy's integral theorem or Cauchy's residue theorem, we are looking at counterclockwise or anti-clockwise directions, okay? Let me just write that down. Counterclockwise or anti-clockwise directions, okay? So this question was a question that was given marks for because they kind of like messed up the options, okay? So you have to be very careful with this term here, okay? So it says counterclockwise when you are applying the Cauchy's residue theorem, okay? You're basically calculating the value for anti-clockwise directions, not clockwise directions, okay? So you have to be very careful about this. This is basically clockwise, okay? So let's move on and let's look at the options, okay? So how do you do this basically? This is basically, I'm sure you must have done a little bit of this. Things like poles and things like that are there, okay, here. So let's look at this, okay? So pole is whenever you have, basically you have here z minus 0 is squared, okay? That's what you have here. I can write it this way too. And you have in your denominator z plus 3. So when is this function going to go to infinity? Where if your z is going to be equal to 0, this function goes off to infinity. If your z is equal to minus 3, this function goes off to infinity. Now, let's look at the question again, okay? C here denotes the unit circle. They've kind of like missed out a C here, okay? C denotes the unit circle. Z is equal to 1 traced in the contour clockwise direction is, okay? In the contour, okay? They actually meant counter, but in the contour means like they're saying that it's clockwise direction, okay? So that's why this question was kind of like given full marks. It should have been counterclockwise direction. Then you could have had a particular answer in this set, but the spelling mistake and all these concepts that came up, it kind of like confuses people. So this is question which was given marks as a result of that, okay? So you have z is equal to 1. Now, which of the poles lie inside the unit circle 1? Okay, so if you have a unit circle 1, basically you have a plus 1 here of radius plus 1. Okay, so one of the poles are here. Okay, one of the poles are here, and another pole is basically outside somewhere. Okay, so it's minus 3. So I will put it somewhere here. Okay, so it's somewhere here. Okay, so it's -3 and this is 0. So now what do? You only take the poles inside the contour while you're calculating the integral. Okay, so let's look a bit into that. So integral, what do you have? You have, when you're calculating your integral, you basically have something called the Cauchy's residue theorem. Okay, so basically it's trying to find out, it's a pretty simple way to calculate the integral. Okay, so it's 2 pi I times the residue at z is equal to 0. And in this case, you do not have residue at -3. Okay, why is that? Because if it was, say, a circle of radius 4, okay, if it was a circle of radius 4, then you could have written residue at z is equal to -3 too. But since it's a circle of radius 1, you can only put in one pole of it. So it's just going to be this. Okay, so I will quickly show you how these calculations are done. Okay, so this is your Cauchy's residue theorem. Okay, so this is times actually. Okay, times the sum of the residue. So your Cauchy's residue theorem, integral of C f of z dz is equal to 2 pi I times the sum of the residues of f of z at the singular point enclosed by C. Okay, so let's look at the next one. Okay, so you should remember that it has positive orientation, which means that it is traversed counterclockwise. So positive orientation implies you have counterclockwise. So if you have been given something like that and you calculate the value, you're basically getting the counterclockwise direction value. You would have to multiply it with a negative sign in order to get something that has clockwise direction. Okay, so that was the confusion here in this question. So this is how you can calculate it. This is your residue at z is equal to 0. Okay, so you need to calculate this. So basically this residue is, there is a particular coefficient in your Laurent series. Okay, Laurent series. And in that you have a particular coefficient where you have a -1. Okay, so go look it up, look at your complex analysis notes and check it out. Okay, so here you have z0, z02 is equal to -3, which is a pole outside the contour. So you don't include that one's residue. What do you end up getting here? Okay, so you now need to calculate the pole. And this is the general formula for a pole of any order. What do you mean by order? It's like the power of this term that you have here. So basically the pole here, which is 0, has an order 2. Okay, so it's because it's z minus 0 whole squared. So you'll have to do that calculation using this formula. Basically, you have 1 divided by m minus 1 for factorial, limit of z tends to z0, dm minus 1 divided by dzm minus 1. That's basically one order less than the order of the pole. Okay, so you multiply this with z minus z0 whole square. Here you realize it's z square into f of z. So you multiply this, the z squares kind of get cancelled out, and then you have to evaluate your next set. Okay, so basically you multiply this is the simplification of the whole thing, and you end up getting -1/9. So you got the residue for your z is equal to 0. Okay, just simplify this and you'll get your -1/9. So basically you have 2 pi I into -1 divided by 9. You have -2 pi I divided by 9. So this is actually there in the options. But because of the mistake that they made was a typo, instead of counter, they wrote contour. Okay, so instead of counter, they wrote contour. And because of that, people thought it was clockwise, and it does not fit in any of the options. So you have basically plus 2 pi I divided by 9. Okay, so if it was clockwise, it would be 2 pi I divided by 9, which was not there in the options. Okay, so that's the reason why they kind of like gave grace marks for this question. Okay, so yeah, so that's the answer. Now let's look at this. Okay, this is something that we all know. We've done it in BSc too. Basically, what do you mean by okay, so let me just write down all these things. Okay, so you have the vectors A and B, which are linearly independent. The vectors A and B are linearly dependent. The vectors A and B are orthogonal. The vectors A and B are normalized. Okay, so you have a vector A and you have a vector B. Okay, so you have a vector A and vector B. Now you need to check if they are linearly independent. So what do? The quickest way to do this is, can I write B times something is equal to A? Or can I write A times something is equal to B? That's the quickest way to look into it. If I can write it that way, then they are kind of like linearly dependent. If I cannot write it that way, they are linearly independent. Okay, there is another way to do this, okay, is to find out the determinant of these two. Basically, you put these two vectors in, okay, and then you kind of like find the determinant of that. If that is equal to 0, then they are linearly dependent. If they are not equal to 0, they are linearly independent. Now, what do you mean by orthogonal? You just take the dot product and you look at it. If they are normalized, when you do the 6 squared plus 9 squared, when you kind of like try to take out the magnitude, they should have a magnitude 1. So that's basically how you check if it's orthogonal or normalized. Okay, so let's move to this. Okay, so a set of vectors is linearly dependent if one of the vectors is a linear combination of the other. So basically you check if the determinant is 0, and in this case the determinant is 0, so you can do that. Or the easiest other way to look at it is basically I can write this vector as, let me check. Okay, so here you have, I can write this vector as A vector is equal to minus 3 times the B vector, right? I can write this that way. Okay, so I end up getting the A vector. So basically these are dependent on one another. Okay, so that's the quickest way to check about dependent and linearly dependent. This is like the most formal way to check if they are dependent or linearly independent. Okay. Okay, so I think I made a typo here. This should have been the two vectors are linearly dependent, not independent. Okay, so let's move on to the next option. Next question. Okay. Okay. So the constraints that can be expressed in terms of an equation related to coordinates of system and time. Okay. So basically, is it your holonomic constraint, non-holonomic constraint, scleronomous constraint, or reonomous constraint? Okay. So let's just discuss about these holonomic constraints. So basically, when you're looking at your holonomic constraints, you're looking at an equation. Okay. Holonomic means equation. Non-holonomic, you're looking at inequality. Basically, you end up with things like inequality. Okay, so you end up things with like less than or equal to, greater than or equal to, less than, greater than. Okay, so those kind of things involve, those kind of equations are basically your non-holonomic constraints. Whenever you have an equal to, you end up getting a holonomic constraint. So the typical example is ball passing through a sphere. Okay, not passing through, going around a sphere. Okay, or tracing a sphere. Or another thing is ball falling off a sphere. So basically this can be any amount. Okay, so if this is your radius, you basically have something like r square should be equal to a square, let's just say that. Okay, and if this is the case, your r square should be less than or equal to a square, or things like that. So this is basically your holonomic and this is your non-holonomic. Okay, so that's the example that's given here. Let's look at, okay, so this is an important point. Your velocity dependent constraints are not usually holonomic. Okay, velocity dependent constraints are not usually holonomic. Basically what you end up having is you'd have some function q, q dot, and t. Okay, so n of them, I'm just writing this for simplicity, is equal to 0, are not holonomic even though they have this equal to sign. Okay, even though they have the equal to sign, that's like an exception. Okay, so now let's look at scleronomous. So these are equations of constraints which are not explicitly dependent on time. And then your reonomous are basically equations of constraint that contain time as an explicit variable. Now, we've kind of like discussed this. So now let's look at this. You are bound to get confused with this term, reonomous, since they've said an equation relating to the coordinates of system and time, you are going to automatically tick reonomous because they have these explicit time things involved. Okay, so but that's not the case. Okay, the case is they've said equation relating to coordinates of system and time. So this word equation is particularly important here. So you have an f, let's say q t is equal to 0. Okay, so I'm not writing all of the q's, I'm just writing one q. Okay, so let's just take that as for n number of q's. So this kind of an equation relating coordinates of system and time is called your holonomic. So it's going to be option A. Okay, so that's that. Now this is very easy. The Lagrangian is a function of what? Okay, so this you all know now by now. Basically it's a function of those particular generalized coordinates and the derivatives. Let's just talk about it that way. Okay, now let's not just say position and that velocities. Let's not just say that. Okay, so let's say generalized position and generalized velocities. Okay, basically generalized position and time derivatives of generalized position. Okay, so that's what your Lagrangian is a function of. So you will see that that is option B. Okay, Lagrangian is a function of generalized coordinates and their time derivatives and time, and contains information about the dynamics of the system. So that's what your Lagrangian does. So that's this very simple question. Now in this question, I think you might have done a derivation on it. Okay, so let's just go through it in a gist. Okay, let's just go through it quickly. Okay, so these are the things that you have. Okay, the repulsive inverse square forces. The shape for the repulsive inverse square forces, the shape of the orbit is hyperbolic, elliptical, circular, and parabolic. Okay, so this is how your inverse square force is written, right? F is equal to alpha divided by r square for a constant alpha which is negative. Okay, which is negative for an attractive force and positive for a repulsive one. So basically it's the opposite of what you think. Okay, so attractive you immediately associate it with a positive sign, but it's not that. It's basically a negative force. And repulsive is one that is associated with a positive force. Okay, so let's move on. Okay, so the thing is that whenever you have an attractive force, you're going to get three types of conic sections, which is your ellipse, hyperbola, or parabola. Whenever you have a repulsive force, that means you have your positive force. Okay, whenever that happens, you're going to end up getting a hyperbola. And these values basically depend on the energies that are associated with it. So if it is required, I kind of like describe the derivation for you. Okay, probably whenever we get a little more time, when the questions are not so time consuming, I will kind of like explain and tell you why these kind of like move from one layer to another and things like that. So basically there is a potential curve, and what you see is the potential curve kind of like traces an ellipse because of the points of inflection that are there. So that's what you're going to see. I'm not going to talk too much about that. For now, if you have an attractive force, you have a negative sign that is associated with it. That means you end up getting your orbit as an ellipse, hyperbola, or parabola. Okay, and let's just keep this in mind. Okay, let's just keep the eccentricity value also in mind, because there are going to be orbit equations involved in such situations. Okay, so if your eccentricity is less than 1, you end up getting an ellipse. If it's greater than 1, you end up getting a hyperbola. And if it's less than or equal to 1, you end up getting a parabola. Okay. And the other case, whenever you have a repulsive force, you end up getting a hyperbola always. So let's look back at the question. What have they said here? They've said for a repulsive inverse square force, the shape of the orbit is always hyperbolic. Okay. In the other situations, you can get different types of conic sections, but here you only get the case whenever it's repulsive, you end up getting a hyperbola. Okay, so if there is no force present, then you end up getting a straight line. Okay, so this is quite easy. You can do it within minutes. Kepler's second law, you all know that it's kind of like related to the aerial velocities. Okay, so basically what you're going to get is the aerial velocity is a constant in this situation. Okay, and yeah, let's just look at all the three statements so that we kind of like refresh our memories on this. Okay, so aerial velocity, the Kepler second law states that the aerial velocity is 0. Aerial velocity is a constant. Angular momentum is not a constant. Linear velocity is a constant. So basically, Okay, so these are the laws that govern planetary motion around the sun. So the orbit of a planet is an ellipse with the sun at one of the two forces. The line segment joining the planet, okay, so let me just draw this for you. The line segment, so you have a planet, this is the sun. The line segment joining the planet sweeps equal areas in equal intervals of time. So if this is probably closer to the orbit, so it's going to be sweeping the same amount of area. If this is covered in a time t, this is also covered in a time t, these two areas are basically equal. Okay, so these two delta A's are basically equal. So that's what you're going to have here. And the last one is basically the time period. Okay, so the ratio of the square of the object's orbital period with the cube of the semi-major axis is the same for all. So what do you have? You have your t square is proportional to r cube. That's what you have here. Okay, so let's move on to the next one. Okay, in Hamiltonian formalism, okay, so how do you write the Hamiltonian in terms of the Lagrangian? I wanted to actually derive this for you, but I think we're running short on time. So I will kind of like, I kind of like hope you kind of like go through these derivations, because it's quite, I mean, like, it's only when you go through the derivation at least once that you kind of like realize, okay, this is how it's going to be. Just go through it once. You would have certainly done this. If you haven't, and if you don't have the notes, tell me, I will forward you the thing that I have. Okay, so basically you have this, and this is an important formula to remember, because people are going to ask you how to find the Hamiltonian and give you the Lagrangian. Okay, so it's quite an important formula to remember. So it's going to be pk qk dot minus L. Okay, so summation of pk qk dot minus L, it's option A. So this is how your Hamiltonian function is given to you in terms of your Lagrangian. Okay, so next let's look at this. So this is something that very few people learn. Okay, it's something that people try to leave out because of the complicated nature of the whole thing. Okay, so I don't know if you've learned this. It's called the Hamilton-Jacobi equation. Okay, so basically when you're looking at transformations, which we learned before, your canonical transformations, what's happening there is we never looked at the time dependence. Okay, we never looked at a time dependent Hamiltonian. And when you look at time dependent Hamiltonians, you basically end up looking at something called the Hamilton-Jacobi equation. And using that, you can kind of like, you can do a lot of manipulation with that kind of an equation, okay? Because you can use it for time-dependent Hamiltonians. Okay, so let's just quickly go through this. Okay, so the Hamilton's principal function, okay? So I'm going to tell you this is called the action, okay? So I think this is how you describe an action, integral of the Lagrangian with respect to time. Okay, so this is how your action looks, and your Hamilton's principal function is basically an action. Okay, then you have a Hamilton's characteristic function, which has other deep consequences. Okay, because this guy is somehow related to this guy. Okay, but this is not dependent on time. Okay, and this is dependent on time. Okay, so it is dependent on time. This is not dependent on time. Okay, so let's look at this. Okay, so you have an S is equal to W, S is equal to ET, S is equal to W plus ET, S is equal to W minus ET. So you get confused because your E is basically some kind of a constant. Okay, so in the text I was referring to, this is alpha, but it is also an energy term. Okay, so basically it is energy. Okay, but in the textbook that I was referring to, it was basically alpha. So I think if you choose the Hamilton-Jacobi equation for something like your simple harmonic motion, you're going to be getting a particular equation which looks like this. Okay, so it's going to be in this form, but you won't really recognize it. Okay, so I think I will kind of like write that down for you once we kind of like look at this. So why do we need the Hamilton-Jacobi equation? Basically, when your Hamiltonian involves time, you require this Hamilton-Jacobi equation. Okay, that's how you kind of like work with systems which have time-dependent Hamiltonian. So here, what you're basically going to do is kind of like run through the derivation. Okay, so basically you're taking an F2 function. Okay, you remember the functions, right? You remember the generating functions F1, F2, F3, F4. So here you basically had a Q, and you had another Q, I think. Okay, so this was identity transformation, if you recall. Okay, so now you have this giving you S, which is the action integral, okay, called the Hamilton's principal function. Okay, so from this you basically look at a couple of partial derivatives and equate it and things like that. Okay, and then you end up getting a Hamilton-Jacobi equation. Now you basically, what you do is you use that Hamilton-Jacobi equation to kind of look at analyzing different time-dependent systems. Okay, so I think I can write one particular system for you here, like one particular system, so that you can kind of like look at how familiar these terms are. Okay, so let's just look at this. You have an S equal to integral, okay, root of 2m into capital E. Okay, it's basically alpha in my text. Okay, so I'm going to put it as capital E so that you can understand what it is all about. Q square and dq. Okay, and then you have minus alpha t. So this is basically the action integral for a harmonic oscillator, and you might have done the solution. Very few people do it, like they kind of like ignore it, saying they've already done so much of the syllabus, they're not going to get this question. Even if they get this question, we are not going to write it, but it is something that is part of your syllabus, so I suggest you go look at it. So this is your solution for the harmonic oscillator. Okay, this is using the Hamilton-Jacobi equation. So what you realize is, okay, let's just check this out. Okay, so this should have been an E, not an alpha. Okay, so this is basically something called the Hamilton's characteristic function. Okay, it's called W of, it's a function of what? It's a function of Q and E. And here you have something that's just minus ET. So basically you get this form, S is equal to W, Q, E minus ET. So what I'm going to do is, you're not going to really ask me, I mean, like nobody has really got back to me on any things that I've put forth. So what I'm going to do is, if you kind of like ask me about this, okay, just for the harmonic oscillator, I will share that sheet with you. Okay, so far nobody has like asked me on extra stuff or things like that, like if they wanted notes for particular things or anything like that. So just kind of like go and check this out, because it's quite important. Okay, so it kind of like helps you solve a lot of time dependent Hamiltonians. Okay, systems with time dependent Hamiltonians. Okay, so the Hamilton's principal function S can be written as a first part, which I kind of like showed you. Okay, it can be written as a function of this Q and E, okay, called the Hamilton's characteristic function, and a second part which was E and T. So let me just kind of like do it again. S is equal to W QE minus ET. Okay, so this is that equation that you have. So let's just go back. You realize it's option D. Okay, this is quite a huge derivation, but I think you can learn it by just applying this Hamilton-Jacobi formula to your simple harmonic oscillator. Okay, so I think that's the way to go about it, so that you remember, you can actually see that the action integral is a function of this Hamilton's characteristic function and this other term, E and T. So what you kind of see is this E is basically the energy of a conservative system. Okay, so basically the E or the alpha that I talked about, it's kind of like the function of your conservative system, and it's a constant. Okay, so let's move on to the last question, I think. Okay. Okay, so this, I think we kind of like found the canonical momentum for a charged particle in an electromagnetic field in the last couple of papers. Okay, I don't know if you've gone through the derivation, but I think it's kind of like worth spending some time on this. So I'm going to go a little extra today. Okay, I've kind of like passed the time already, but I'm going to like kind of like go step by step, because I just gave you the derivation and said read it. Okay, so these are velocity dependent potentials. Okay, so I think I told you about this. This is basically in CGS units. Okay, we're going to be writing the Lorentz force. So F is equal to Q E vector plus V cross B divided by C in CGS units. Then you're going to be taking the electric field, which is expressed in terms of your electric scalar potential and your magnetic vector potential. So this 1 by C becomes up because it is mentioned in CGS units or your Gaussian units. Okay. So it's very, the thing is that most of the old textbooks have this kind of a notation and they kind of like follow it. So all the questions that come up are basically going to have this kind of a form. Okay. So basically see that in your options, you kind of see that there is a C here. Okay. So even without the C, this is actually correct, but then it would be in SI units. Okay. So let's move on. Okay, so I think I showed you that these electric fields can be written in terms of these potentials and the magnetic fields can be written in terms of these potentials. So I'm going to substitute these into this force. Okay, so the force is kind of like written in terms of potentials. Okay, now I substituted the electric field, which is your del phi minus 1 divided by C dou A vector divided by dou T plus 1 by C D vector crossed with del crossed with A. So this is basically something called the back cab rule. Okay, so the curl of a curl, I can write it as, okay, I can write it as BAC minus CAB. Okay, it's called the back cab rule, and that's what I'll be using next. Okay, to kind of like simplify this. Before that, what I need to do is I need to simplify this into a certain value so that I can cancel off a couple of terms. So this partial derivative, I can basically write it into dou A vector divided by dou T. I'm not really doing any change here, okay, because I have a dou x by dou T. If I cancel this off, I end up getting a dA by dt, okay. So basically, I'm just multiplying with these dou x, dou y, and dou z. Okay, and you know this term basically represents velocity. So this is velocity along x direction, velocity along the y direction, and velocity along the z direction. So now you have dou A vector divided by dou T plus, what can I write this as? I can write this as basically, okay, so what acts on your scalar? Okay, so basically the thing that acts on your scalar is a gradient. Okay, gradient acts on a scalar and divergence acts on a vector. Right? Did I say that wrong? No, the gradient acts on a vector and the divergence acts on the scalar. Okay, I think I messed that up pretty badly. Okay, okay, so here you have a V and you've got a dot product of that. And then you have a vector A. Okay, so now how do I simplify that further? Okay, so now here what you realize is I kind of like wrote this for dA vector divided by dt. Okay, so I'm going to take this dou A vector by dou T to the other side because I need to kind of like replace this dou A vector by dou T here. Okay, then what do? I told you about this back cab rule. So I kind of like have to use that. Okay, so basically this is A cross B cross C. Okay, and what do I have here? I have a B. Okay, so I take B and put this outside. And then I have A. So that's going to be B. And then I have C. So that's going to be A. Okay. And then similarly, I have C, so I put A here, okay, and I have A and B, so that's going to be A, which is that, B dotted with B, okay. Now, let me ask you another thing, okay. So when you write dot products, you can kind of, they commute, so you can interchange them and nothing would happen, okay. So you basically end up writing B dot del, okay, into A. Okay, so this can be done. Okay, you can interchange these two. Still fine because they commute. Okay, so let's move on to this. Okay, so now you kind of like substitute these values here. You have had this similar term and this kind of a term, so you end up canceling them because there's a negative sign involved in it. Okay, and then you write okay, and then you kind of like combine this. So now what you see is you kind of like have to add a couple of terms here in order to get this d by dt of del v. Now the thing is that what you're doing is basically taking this and writing it down here. Okay, so this term is basically being written down here in a different way with a operator that looks like this. Okay, so you've got I cap, j cap, and k cap. Okay, so this is basically to do with velocities. Okay, so this lambda operator. Okay, so now what you realize is when you take the divergence of your when you take the gradient, okay, sorry, gradient of a scalar function. So when you take the gradient of your scalar, you're taking this gradient of a velocity. So you're basically looking at a velocity gradient here. Okay, so that's equal to 0 because when you do a dou by dou Vx of your phi, you're going to get a 0. Okay, so I hope you get that. Dou by dou Vx of phi is equal to 0. Okay, similarly, dou by dou, similarly, you get y and you get z. Okay, so same thing applies for all of them. So even if you add a term called del v phi, it's not going to make any difference. Okay, so it's basically 0. It's not going to make any difference. So kind of, let's just work this backwards. Okay, so if I have a d by dt of del v phi, it's not going to make any difference. It's still 0. Okay, so this term is basically 0, just this term. Now let me look at this term. I do a del v of v dot a vector. I end up getting an a vector because let's say when you're applying a vx with an a vector, a vy with your a vector, and vz with an a vector. Okay, so let me just have ax, ay, and az because you're taking the dot products there. Okay, and you kind of differentiate it. All that remains is an axi cap plus ay j cap plus az k cap. I hope you kind of like go and work it out because it's probably very useful for the next semesters that are coming up. Okay, and it's kind of like a useful, nice tool to remember too. Okay, so what do you end up seeing? You end up seeing that if I kind of like apply this operator here, I'm going to get a vector A. So basically I end up still with a minus 1 by c d by dt of A vector. Okay, so that's this part. And now what do I do? Okay, so what do you see here? You kind of like see that this is basically a potential. This is basically a potential U. Okay. And what is the Lagrangian? The Lagrangian is equal to t minus u. So basically you end up getting L is equal to t minus phi minus 1 divided by c v vector dotted with a vector. Okay, so that's going to be a plus because you have something like this. And you also have a q outside, so I will multiply this with a q. Okay, so now let's go back to the question. Okay, let's erase all this. Let's erase this too. Okay, so let's just leave this so that we can kind of like verify it with the question that we have. Okay, so you basically have t minus this q is basically e. So e phi plus e divided by c v dot a or a dot v. It really doesn't matter. Okay, so let's move on to the last part. Okay, so what did you do last time? You basically found out the canonical momentum. So you have to remember that Lagrangian, it's very important. Okay, so let's look at this. Okay, so you can write this f as basically you end up writing this when you don't have time involved in it. Okay, so if you look at most velocity dependent potentials, you have this time derivative of the potential when you look at your force. Okay, so here you have u is equal to q into phi minus 1 by c v vector dotted with your a vector, and this is what you have. Okay, so you basically have t minus v and you kind of like found out your Lagrangian. Now what you did after in the previous set of papers was basically you kind of like found out the canonical momentum. Okay, so you basically did you basically took the derivative of the Lagrangian with respect to time. Okay, and then you took it with respect to the time derivative of your coordinate to kind of like find out just the canonical momentum. I hope you kind of like recall this part. Okay, we had something like this in the options: m v vector plus q divided by c a vector. So this is the canonical momentum. How do you get that? Basically, to get your canonical momentum, you take dou L divided by dou Q dot. Okay, that's basically the velocity gradient that they're doing here is basically dou by dou V, because your Q dot is basically V, right? It's base velocity. So that's what you're doing here. Okay, so this is the last slide that you have.